Hello everyone, and welcome to another Do development video. For those who don't know, Do is my sort of toy programming language, and it's a stack-based functional programming language. So if you know about Porth or Forth or even Factor or Joy, these are all stack-based languages where rather than having expressions, binary expressions, statements, and blocks and loops and stuff, you have just a stack. And doing something like 4, 5 plus print will push these values. In fact, let me open, let's see, what is it? Target, debug, do. We have a REPL. And since last time, I've sort of juiced up the REPL a little bit. In fact, it now uses this as the sort of like input character, or like the input sigil, and I really liked it, so I made it the logo of the language, because every official language needs a logo, or else it's not a real language. And also I juiced up the README a bit. We'll get to that in a second. So if you go into the REPL and I type 4. It now ghosts in what's on the stack. So we now have 4 on the stack, and if I write 5, I now have 4 and 5 on the stack. And if I do plus, that pops off 2 values off the stack and adds them, and then pushes the result back onto the stack. So now we have 9. And I could do 2 times. But it's also it's a functional language, so I can pop that, and I can take this example here. So I can take a whole list and push it onto the stack. And so this is a single value. So if I push another 5 and then I swap them, it puts the list on top. So let me get rid of that 5. And then I can push a whole function onto the stack. So dupe star, this is like my hello world do program. Dupe star squares a number, and it duplicates the number, times it by itself, and then pushes the result onto the stack. And then this is also a single value that I can, manipulate as if it were just one value on a stack. And then with that, I can do higher order functions like map. And what this does is it takes a function and it takes a list and applies the function to every element in the list to return a new list of transformed values. So it squares every element in the list. And then I can print the value. So when it's grey, it's just ghosting in what's on the stack, and then when you print, it pops the top of the stack and prints it, which you can see if I push many values and I type print, it just prints the top and then shows you the rest of the stack. So that's do. And since last part, there's been a whole scrapped episode. And not because it was bad or anything, it's just because it didn't really go anywhere. But we did learn, I did learn that my current approach to the interpreter, which is what's powering the REPL, just wasn't good enough to do things that I wanted do to be able to do. Such as control flow. So the way that this interpreter works is it's kind of a cheat. So we have this interpreter which just has a stack of values, and these values are very much not single values. It's just a complex stack that doesn't really match how it would work on a real CPU, and it kind of just it interprets it instruction by instruction, which is fine for now, but you can't do control flow. You can't jump arbitrarily in this program. So I invented another language. That's the clickbait title. I implemented, or I invented another language for my programming language. And so I basically implemented do bytecode. And I did this over the course of a couple of days off camera because it was just a lot of trial and error, and it was just hours of me just failing at getting this to work. And it finally kind of works. And so I stopped developing off camera as soon as I got something promising so that I could do this. So if you don't know what bytecode is, if you know Java, or if you're really hipster and you know Erlang, these are like, they're interpreted languages that get interpreted on their bytecode, which is like a simplified, stripped down version of the language that is easier to interpret, or it's more convenient to interpret than just the high level constructs of the language. So you notice in bytecode there isn't any operation that is map, because you can implement map, and by that logic you can implement any higher order function so far using just these instructions. So if we ignore the ones that are like just the intrinsics that you would normally get in any programming language, we have push and pop. We have some nice ones around dealing with lists. You can push a block, and you see it pushes sort of the index of the block, not the actual block itself. So this is like the index of the block, and then you can then backpatch it to work out the address that that block starts, and you can jump to that block. Load and store will basically save a value from the stack that you can then push later. And this is where the topic of today's video is going to mostly focus, because this isn't really implemented yet. We skip all of the intrinsics. I have some nice functions around, or some nice operations around printing, but I would like it if it was just a single value, or even if this was an intrinsic that gets called by call. Label, so you can jump to a label, and it has a operand which is its index. And then, call, jumping, so unconditional jump, and a conditional jump, and a return. And using these instructions, so if we skip this stuff which just kind of like encodes and then decodes to binary, which isn't very useful at the moment, you have a lowerer. And it's a really basic, crappy lowerer at the moment. So I'm basing this kind of on a Java bytecode compiler, where it kind of builds up a constant pool of values that then you can refer to statically when you are emitting the assembly. So for instance, like a function name. You emit the function, you get its name, and then you save its address so you can jump to it later. That sort of thing. And it basically just goes through every typed operation. So now the type checker emits typed operations, so the type that you are producing or consuming from the stack. And it produces this funky type, which I think should just be like a stack frame. And we're going to get onto that, because I think what we need is the concept of stack frames, where every stack frame knows how many local variables it produces, so that we can offset a certain register. I think it's RBP is the register, or RSP. I think it's you set it to the base pointer for your stack frame, and then your RSP you can store all the locals on. That is my understanding. That's what we're going to be implementing. So this is probably going to need to be a bit more complex, but it's basically like the name of the block. So usually it's a function, and then the list of the list of instructions inside that block, and then it's just a list of them. And it currently fakes having a main function. Maybe I will amend that in future, but it's really nice to have it sort of like pseudo scripting or pseudo script like language, scripting language. Where like Python, where you can just start typing things and then you can have a main function if you want. And then this is the interesting thing, is like one typed operation can potentially be many bytecode instructions. And in fact, it has to be for certain more complicated instructions. Like pushing a list isn't just push a list, it's push every element in reverse onto the stack, push the length of the list, and then new list, and new list, like I stole this from Java bytecode. It's basically just an intrinsic that pops a number from the stack, and then pops that many elements from the stack, allocates them on the heap, and then pushes the pointer to that list. So lists are now kind of heap allocated, which is its own can of worms, because now you kind of need to know when a list is no longer referred to. And so you can kind of, every time you pop a list, you can free it because the language is functional, so things are immutable. So when you duplicate a list, you're actually copying the list. So I guess, yeah, when you pop a list, you can free that memory. Okay, that's good to remember. I think I didn't implement that because originally duplicating copied the pointer, but you don't want that because, you know, if you have two lists on the stack and you modify one, you don't want to modify the other. And as it's gone, I've now kind of made everything immutable, which is kind of how functional programming languages like to be. So that works. But this is the juicy bit. So if I was to go back and interpret, so the -i flag interprets a file, and I interpret list do, it works. And so the interpreter now, so the interpreter when you do this type of interpretation is using bytecode. The REPL is currently using the old interpreter because you just get nicer printing. If I was to use the bytecode interpreter, instead of seeing the list, you would see the pointer, which is more like the index that the list is stored at on the fake heap. So this interprets the list, and it does a map which was implemented using all of these operations, which is insane that it works. And I was so happy when this worked. And we can go through how it works, and I need to remind myself how it works. But the like main idea is you start with a list and a function, and they're both pointers on the stack. So if you go back here, you have a list and you have a function, and they're implemented by them being pointers on the stack. And you essentially store both of these in locals. So you're not storing them on the heap, you store them kind of in the stack frame, if that makes sense. Like you start with some amount of stack space, and then a block can say, oh, I have like 3 locals in my stack frame, allocate me 3 more 64-bit values that I can play with, and I won't clobber anyone else's stuff. That will probably make more sense as we go. So it stores the function, it stores the list, which pops both of these, but now we have indexes of these values. So then we can load those values back and push them onto the stack. And this doesn't currently work in the compiler, but it when it does work, it will enable us to do map in compilation, and it will enable us to have variables in do, which is something I really want to have, which is basically just going to be the exact same thing. It's just you have the value on the stack, you store it in the locals in some offset, and then when you want to load it, you just reach that offset and you copy that value onto the stack. And also, I just said compiler, and I haven't even shown you the compiler. So currently, I will get back to this. We currently have a emitter, which emits assembly. It emits assembly that will compile with FASM on my machine, which is a 64-bit Windows machine, unfortunately. Just because that's what I have, and that's how I can get this done. So I'm very sorry if you want to try this out and you're not on Windows. I would really like it to have multiple targets and have like a Linux one and a Windows one, but I just don't have the ability to compile to Linux at the moment. And also I'm in uncharted territory as it is with the Windows assembly, so I mean, most of this will be basically the same, but so for each of these bytecode instructions, it's way easier to emit assembly for these instructions than for the higher level operations that we have. So yeah, like for pushing a block, you just get its index, you load the address of that block index, and you just push that that index onto the stack. And then when you want to call, you pop that value into racks. You load that address, and then yeah, you do a bit of crap register management, which we're going to fix, and then you call it. So we have compilation, and I think one of the instructions is incorrect. I think subtract is incorrect, or I think it just doesn't handle. Yeah, it doesn't handle signed subtraction. So if we open up arithmetic do, this is just very simple arithmetic instructions, and I think yeah, I'm going to swap this one round. Is that right? Yeah. So this would be 6 minus 2, I believe. Well, we'll see. If this prints 4, then it should be... So we can go into the interpreter. The interpreter is kind of like the source of truth of like what the behavior should be. So that should be minus 4. Okay, so we want it to be 6, 2. 6, 2 minus... Yeah, we want it to be 4. But currently it's not. So let me show you. If I go to this, and if I do arithmetic, it is 4 if I interpret it in the level of bytecode. Okay, but if I compile it, so there's now, if you have no flags, it will compile to an exe. And if you supply the R flag, it will immediately run the compiled exe, which I think is really handy. And look, it's... let's see. Did this get... Yeah, this got all weird. Hang on. Fucking PowerShell, I swear to God. So if you interpret it, it's 4. But if we run it, it's 2. So something's gone wrong there. But yeah, won't worry about that. Well, we will worry about it eventually. But it compiles. And it compiles by going to this bytecode. And then I've implemented enough emitter instructions, or like emitter code, for the operations that this emits to be able to compile. And I think that's really cool, personally. And yeah, but you can't map. So if I go back to how map is implemented, so we store those and we load and we get the length of that list, and we store that length into a counter, and then we essentially just loop. Let's see. Yeah, here's the loop. So we basically set a label, load the counter, push 0. Is the counter greater than 0? If no, jump to the end. If it is greater than 0, we essentially load the counter again because this consumes it. We decrement it, and we save that value. We load the list. We load that counter, which has been decremented. So remember, it started at the length, which if we try to access that element, that's over the length of the list because it starts at 0, which is why it pushes it and then decrements. So the first time we do list get, we have length minus 1, which will be the final element of the list. So that pushes that onto the stack. And then we load the function, we call the function, and we jump back to condition. And then we do it again. So we load the counter, which has been decremented. Is it greater than 0? If it is, we go again. And we get the next last element. And we're kind of like doing it in reverse order because we want to have it in like the first element at the top of the stack at the end. And when that's all done, We load the list one more time just to get its length on top of the stack. So now we have all of the transformed elements on the stack in reverse order, then the length, and then we can just call new list and create a new list out of all of those. And the bytecode interpreter can interpret that, because it can do store instructions. It can do store instructions badly, but it can do them. If I find, yeah, store and load, it has this sort of like locals array, which is not really how I want to do it. But that's how we can end up correctly interpreting map. And it kind of proves that the bytecode that I emit is correct, because the bytecode interpreter can interpret it. So that's, yeah, another 20 minutes of yapping. But basically that just catches you up. I'll have like time codes on the video, so people will be able to skip if they don't want to worry about this. But that's where we are. And what I really want to do is effectively steal the way that Porth handles local variables, and it is it RB not RBP, RSP. Yeah, retstack RSP. So it effectively, let's see if I can find an example. Yeah, so binding is how Porth does variables, and it consumes a number of elements on the stack and sort of pushes them on the return stack. And when you say, oh, I want one of those values, it kind of reaches to the offset on the stack and puts it onto the current stack. And yeah, so if you push a bind, it Porth is very, very fun to read. But yeah, this is basically what I want to implement. And I need to properly understand how this works so that I can actually implement it myself. So yeah, that is the plan, is to have storing and loading working in the emitter so that I can compile map. And then once I have map, then I can implement variables. And because I'm now emitting bytecode with like labels and jumps and things, this is why I scrapped the last episode, because I tried to implement essentially control flow, ifs and returns and things, and it just wasn't working with the current interpreter, because it doesn't really have labels it can jump to. It doesn't have arbitrary control flow. It just interprets the list of instructions one by one. So if you have a jump, it doesn't know what to do. So that's the plan. I'm going to essentially go formulate how I want this to work, and then we're going to implement it. So I'll see you in a bit. Okay, so I have an idea. I don't know if it's going to work, but we're going to try it. So basically what we need to do is every time we enter essentially a stack frame, we need to subtract from the stack pointer how many locals we expect. So I think this crazy type here, well, I guess this type here, needs to be a stack frame. And I foresee, excuse me, that it's going to be public because I'm going to need to use it in the emitter. So we're going to have a stack frame. So it's going to have instructions, and it's going to have max locals, which is a use size. And effectively what we need to do is I think, we don't want the name in there, so we're going to have a stack frame. And so we're going to have the result be that. Yeah. Okay. So in here we want to create a stack frame, and the instructions are going to be this, and the max locals. We need to sort of build it as we go. So let's set it to 0 for now, and push that, and then yeah. So we want to build a stack frame here as well. So what this is doing is, this is kind of a hack because I don't have like a main function. Because in do you can just sort of start. It probably would make sense to have something, you know, like this. This is how you do functions in do. Oop, that was the wrong way. Is you just say fun, the name, and then you just put it into round brackets. But I kind of like that you can just do this, and like that's how the REPL works. So I think for now this is fine. We'll see how this shakes out. So we're in the lower. So yeah, we basically just start lowering from the start. And then if this ever encounters a function definition, it sticks it into this funds to emit, and then we essentially just create frames for each function. Okay, so let's ignore the case where we define functions. So let's just have a basic so we just want to compile this, essentially. So how do we know how many locals we have? Well, every time we call next const, I suppose, it's kind of... Yeah, I don't think this should be const, because they're not consts, are they? They're variable, they're locals. So actually, yeah, I don't think I use the constant pool properly. I guess I use it properly for blocks. So actually, I think I need a second vector. Or do I? Because I don't need to store anything. I just need to store the count. So if I say locals count as a usize, then I think we have it. So let's see how this goes. So we start with 0, and then yeah, we can just do self locals count, and then we can do that here as well. And then after we've emitted, or after we've created a stack frame, we just reset the locals count. Again, I don't know if this is a good way to do it. We're just going to do it and see if it works. And then once we've proven that that works, then we can go and sort of tidy up. So I've had some experience trying to emit Java bytecode before. And you kind of have there's like a nice library that does this all for you. We don't have that. So eventually it would be nice if I had a type, or you know, some sort of module in this which acts like a bytecode emitter, where you essentially just like visit instructions and it will compute the stacks for you. Sorry, the stack frames for you. But right now we're just experimenting. So next const, we just want something which is fun, very similar to next label actually. So it'd be next local, or you know, something like that. And it's effectively just the same as this. So we would just say let local equal self locals count. Yep. Increment it by 1, and then return it. Okay. So, duplicate list also would probably use it. So, in fact, let's implement this with duplicate list first, because that's a simpler example. So duplicate list, rather than just, like I said, duplicating the pointer, it copies the elements of the list. So if I go to list do and I dupe print, I think I've broken main. Yeah, because this doesn't want a stack frame. So let's make it want a stack frame. And that's broken this. For instruction in function, it needs to be public inside stack frame. Actually, I don't think we need... Yeah, we do need max locals to be public. Yeah. Okay. So stack frames are public. So for instruction in function, instructions. Why does it hate that? Oh, because it's no longer borrowed. Oh, but we want to borrow it. Boo. Okay. So that works. Right. And then we also broke compilation, I assume. Yeah. So actually, this is where we want it. So we want to emit a stack frame. And file pin bytecode instructions. And we want to borrow it. Cool. That compiles. So, go back to this. We want to, and in fact, why don't we print how many locals we made? So in the LoRa here, let's actually just println stack frame has stack frame max locals is this. Okay, so that's not going to do anything at the moment. But so if we interpret this with the bytecode interpreter, list do, you see it prints two lists. If I let's see, because I can't mutate lists, so maybe it's okay to duplicate the pointer. Whatever, we'll use this as the example. So if I cargo build, wow, can't type, and then do that, we have 0 locals because we never actually created locals. So if we go back to the LoRa, yeah, man, I'm kind of dubious of this because it would be so much quicker to duplicate if you just duplicate the pointer. But then it makes freeing the memory really hard. So yeah, we'll keep this for now. So instead of saying next con, and also this kind of irked me. I was like, why do I need to name these? Because I never omit this name, and this is why, because they're not named consts. They're locals, and locals. Ooh, maybe locals will need names because when you have variables, and this doesn't actually take any arguments. Yeah, so that also irked me a bit. Because it's like label, yeah, you just ask for a local. So if I do it again, stack frame max locals too. How about that? Okay, so in the emitter, so I'm pretty sure if I try to compile list do, it's going to tell me I haven't implemented store and load. Yep, I haven't implemented store. So let's bloody implement it. So the first thing we want to do when we enter a stack frame is we want to subtract, or we want to save the base pointer. So there's the register RBP, which is the I think it's register base pointer is what it stands for. So we want to so let's not call this bytecode anymore. Let's call this frame. Yeah, and for op in frame instructions. Yeah. Okay. Yeah, I have some very hacky. Yeah, I have some very hacky stuff. We currently it passes arguments between functions using the registers properly, but we need it to use the stack. But we're not worrying about calling functions for now. So we enter a frame. We align the stack to 16 bytes, which apparently is a Windows ABI requirement. Yeah, this is a bit scuffed. So we won't worry about this. In fact, I'm just going to say to do functions are not yet implemented, because that was all wrong, basically. So we want to subtract from RSP the number of locals. So we want to store, I believe we want to store RBP, RBP in, let me see, let me check my notes. Yeah, that's it. So we essentially push RBP onto the stack. So when we enter a function, we save the base pointer so that we can restore it when we're done. And then we move RSP RBP. I have like pseudocode here. No, other way around. So we move, that to there. And then we basically subtract from RSP, frame max locals times 8 for 64 bits. So this is called phasm emitter, but it should be like Windows 64-bit phasm emitter. And that should be it. So when we when we want to access the locals, we use RBP, I believe. Check my notes again. Yeah. So now RBP is our base pointer. So our stack is gonna start at RBP. If we have 2 locals, we subtract 16. So we have a window of 16 bytes at RBP, and our stack pointer is down here. So as we push values onto the stack, we're pushing them down here, and then we want to get our locals, they're in this space here. And then when we leave this function, we want to clean up. So we want to add. So when we leave, So I think, we don't want to. This is to return values. This is stupid. We don't worry about that. Actually, we maybe do want to worry about that because that will break dupe. But yeah, to do use stack to return values. I don't think we need to worry about RBX. Because we're no longer worrying about RBX up here. Yeah, that was just, I feel like that was just kind of like a band-aid or a plaster. Sorry, I'm speaking English here, British English. To get the function calls working. But I think I shouldn't be using the registers, I should just be using the stack because, it's a stack-based language. Okay, so when we're done, when we return, we want to essentially reset this. So we want to add back onto the stack pointer. Is that true? Maybe we don't, because return will actually just use RBP. Yeah. So I don't think we need to worry about that. Okay. So store. Let's go to store. We have an index. So RSP. If we have a look, or RBP, sorry. RBP stores our like stack frame base. So we want to, we have something on the stack. So we have value on the stack. We want to pop that value. We want to pop that value into racks, I guess. So we'll do that. And then we want to move mov racks into RBP minus 8 times the index. So index times 8. Because if it's the 0th local, then we just want to be at RBP. If it's the first local, you want to be at RBP minus 8, and so on and so on. And then I think the loading is just the opposite. So get the index. We want to push this. Is that right? No. No. We can't do that. We want to mov that into racks first. And then push racks. I believe that will do. We want to do that. So, that could be it. Oh, it compiled. Does it actually work? It's actually let me. So it's a bit buggy at the moment. It will say it compiled to list.exe. Yeah, but it didn't. So let's see. Why didn't it like that? Illegal instruction move. Oh, for God's sake. Like, I don't understand the obsession with it being mov when there's already 4-letter instructions. For God's sake. Mov. So yeah, it says compiled, but it actually failed, and that's because let's see. If this command fails, it doesn't, because the result is whether or not there was an output. So I feel like I need to I wonder actually if I get the result and I do this. Do that. Well, I mean, now I fixed the bug, so... look, it still didn't work. See, this is really annoying. I feel like I need to, like, eprint line std error as well. There we go. Illegal instruction, label 0. Yep, it needs a colon. Ooh, that's interesting. So label 0. That, if we go back to the implementation of duplicate list, yeah, label, cond, because this would have been 0. So I implemented that wrong. So if I go to label, that needs a colon. Great. Process.loop symbol already defined. Ooh, okay. Where is that getting emitted? Because there shouldn't be a label called loop twice. I see. So where are you getting emitted? Yeah. Oh, in... New list. Oh, because I call new list multiple times. Aha, yeah. See? That's dumb. So new list, I think, should actually be implemented in bytecode, because yeah, I can't do new list twice because I use the same label. Oh, for God's sake. What if I bodge it for now? This is absolutely, in fact, to do this is just a massive hack to emit multiple new list hops. So if we go to loop, and this is in print list, we want this one. Do that, and then self labels plus equal 1. And actually we want to do that after this because we want to jump to there. Super big hack, but this isn't production code. We just want it to work, and then we can go from there. End. Okay. This is where it starts to break down. So let loop label equal self labels plus equal 1, and come on, and then yeah, end. Okay, so we want to do that and do that. This is horrendous, by the way. Don't write code like this. But this just proves that new list probably shouldn't be a intrinsic like this. Maybe it should. We should just implement it more cleverly. Undefined symbol label 1. Jump if false label 1. I feel like we want to jump there, no? So what's this? Man. Maybe this was a terrible example to use. Yeah. What if we just tried this? Function not implemented. Damn it! Okay. So, go back to this. So yeah, we're really scuffing it with these. Oh. Yeah, with these manual labels. Yeah. Okay, I'm going to take a quick break, and I'm going to find where this is being done, and I'm going to do it properly. So, be back in a second. Okay, I'm an idiot. It's actually fine. It's just this doesn't have a dot before it. Okay. So, where do we emit JZ? Jump if false. God damn. Okay. What next? Jump label 0. Yeah, because we don't Do that for unconditional jump. It compiled. Does it work? No, but yes. Interesting. Why does it do that? Maybe something wrong with... Yeah, because the interpreter's fine. How odd. Okay. So, emitter. What could we be doing wrong here? So, when we lower duplicate list, we store the list and then load it back onto the stack and we get the len. In fact, let's compare this to the assembly. So we want our first store instruction, probably index 0. Yeah, here we go. Because this is the end of creating a list. Yeah, so let's get list to do. So we're creating a list. So we push in reverse order all the elements. We push the length and we call new list, which does all of this stuff. So actually, if I just print the list, yeah, that works. Because that just creates a new list by pushing it, allocates 32 bits, 32 bytes, and then loops through each element and the length and pushes that to the, or stores that in the array that we just allocated. And RBX holds the pointer, so we just push the pointer, and print list handles that. So if we duplicate and print, something's going wrong. And so the first one we print is actually the duplicated one. The first one we print is the duplicated one, because if we swap, yeah, the duplicated one is a little bit corrupted. Ooh, okay. So something's probably wrong with the lowerer. So let's simplify this again. Just be dupe print, compile that, and let's go through the assembly. So our first store instruction, yeah, this is where we start here. So we store index 0. So we pop. So yeah, we've pushed the pointer to the created array. We pop it into racks and we move that into the first local. Then we immediately load that back and push it to the stack. Yeah, this is what I mean. Like, this is not very efficient assembly code, but it doesn't matter because it works. Well, it doesn't work, but it will. We pop racks. We move the yes, we dereference the pointer, which points to the first value in that array, which is the length, and we push that to the stack. We store that in 1. So that's those 4 ops, and we set the label. We load the counter, which is the length. We push 0. Yeah. We say, is it greater than 0? Otherwise, jump to false, jump to label 1. Yep. Jump. So if 0, jump to label 1, that will skip. So we then load the counter again, push it onto the stack. So we load the counter, we push it, we load the counter. Push it onto the stack. We decrement it. We store it. Hey, okay. So the counter should now be 4. Uh, we can verify this. So on the stack, so we have in racks. So if we push racks and we call print int ln. Yeah. So we should see it print 43210. We want to go from phasm. And then list exe. Ooh, interesting. What? Probably I've messed up the value. Pop racks. Push racks. Let's not. I think I'm messing up the stack. So we do that. We load the list pointer. Push that to the stack. Where are we going? So we've just done the deck. We've stored that. We load the list. We load the counter. We do list get. So on the stack, we have the index. Ooh. Yeah, we increment it because we need to go past the length, because the first element is the length. We pop RBX. So we pop into RBX, which is the list. Yeah. Pop RBX. Move into racks. RBX plus racks times 8. Push racks. Something about this I'm not sure about. How do we do list get? Yeah, see, we're just kind of cheating here. So something about this doesn't feel quite right. I'm going to take another little break and have a look at this because I feel like I've just been staring at code, assembly code for too long. My brain hurts, so I'll be back in a second. Okay, so I'm doubly an idiot. It's because the jump 0 instruction, I thought it was just if the value on the top of the stack is 0, jump, but it's not. It's if the 0 flag is set, which makes way more sense. So all I really needed to do is just pop the stack and test if the value is 0. And then now if I rebuild the... Well, if I rerun the program, it now correctly duplicates what's on the stack. So I then went off and tried to implement this, but I think my stack, like calling functions and stuff like that, is just absolutely buggered because I'm mixing passing stuff by registers and passing stuff by the stack, and I think my assembly is just completely a mess. So I think I'm going to leave it for now to compile this sort of thing. But I think now that we have stack frames, I think it would be nice to implement variables. So I have a bindings.do, but this is kind of like a hypothetical syntax, and I'm not really sure if that's what I want it to look like. So let's just say variables.do. And let's have a think of what variables actually look like. So if we went like the porth route, we would have something like 5 and then let x in and then some code and then an end. And I think we could do similar, just have it inside like a block. And then when you're inside this block, x will basically just push 5. And how this will be implemented is when we see a let, we just look at all of the symbols, and then we pop from the stack, and then if we see one of those symbols inside the block, we know what type it will be, and we can just load the offset. So I think this would be pretty simple to do. So we could do XX plus print, and this will just print the double of whatever's in there. And it's not like a function; it's just it's a scope, really. So actually, we're going to need to add the concept of scopes to our type checker as well. So I think this is a nice example. So let's first of all add the let keyword to our syntax highlighting. There we go, that's better. And let's bloody implement it. So I think I'm going to just make a commit and do compile, store, and load bytecode operations. I think we're going to have a whole episode dedicated to fixing the stack, because I think that's a very interesting topic, and I think it's something I need to learn, because I've basically just been I don't really know how to code in assembly. I'm trying to learn as I do this, and so I started off using like the correct C ABI, or not C ABI, sorry, the Windows ABI, as if you were like coding in C, passing arguments through the registers, but that's just not going to work for do. The arguments and the return values need to be passed via the stack. So I need to smash apart and rebuild how that gets emitted. But I think for now, this should be fine, because our dupe example worked. So I think storing and loading should work for this, and then we get variables in do. So first thing we need is we need a new keyword. Oh yeah, so these were the control flow keywords, if and choice. And actually, I think I have conditionals. Yeah, this is what they look like, and I'm not sure if this is how I really want them to be, but basically if will pop a function and a boolean, and if the boolean is true, it will run the function, and then choice is the same but for two functions. And so if the boolean is false, it will run the second, and if it's true, it will run the first. But this kind of falls apart without being able to do jumps. And then, yeah, doing return is basically impossible without jumps. So that's why I abandoned this. So let's add the let keyword. And I kind of like let as the name for it. Maybe just because I've been in Rust this whole time. But let's add let. So now, when we see the let keyword, we don't emit like a let op. We need to do something similar to parsing blocks and parsing lists. So if we go, yeah, like open square and open parenthesis, wherever that one is. Oh, see, look, we have its own function there. So let's nestle it up near here. So when we see a let, well, it's been a while since I've actually had to do any parsing. So what do we want? We want to, while the current token isn't an open parenthesis. So how do we see what the current is? Yeah, it's been a while since I've had to be in my parser. So while, what do we have? We don't really have like a peak. I think we might have to do this sort of thing. Yeah, pretty much exactly like this. How the lists are parsed. So elements. So this would be bindings. And while it doesn't equal open parenthesis, we push bindings. We don't really want to parse an op. We want to say if let token kind identify. Actually, no, we want to expect. So we want to say self expect identifier, and these are the tokens. Is that? How do I use this? Okay, and then token span, right? Is that right? Because this is, yeah, this is at the fun. So it needs to be the token's cursor, because it's the current this one, because it's the current token we are looking at. Yeah, like that. So then we say identify equals this, and let's put a to do here to shut that up, and then we push the identifier. Yeah, and so bindings is a list of tokens. Okay. And then when we break out of here, we expect an open parenthesis. How do I do it here? Doesn't equal close square. Ah, I don't even check. I just assume. Okay. This feels really janky. Doing tokens. And does this expect it by a reference? And doesn't like that. Expected token. Yeah, I see. You want, of course, I have to actually pass you the tokens. Yeah, that feels a bit janky. In fact, no, I don't even want to do this. I just want to say let block equals self parse block. And that takes the tokens. Why does it not like that? Oh, it does need the open paren. Okay, so let open paren equals self expect token token kind. See, this is what I mean. I haven't been in my parser for so long because all of the new operations have just been like keywords, or like all the new stuff I've been adding has just been like the compilation. So then tokens and then token self cursor span. Yeah, I still don't feel good about that, but so we take the tokens, take the open paren, other way around. Expected, so yeah, we would give it by reference, and then we get the block. Okay. So let's just confirm that we have what we expect, and that this even works. So let's print our bindings, or print our block. Because I'm suspicious of this. I feel like this is going to be off by 1 or something, and I feel like I need to do this in a better way. So we rebuild, and then we want to compile resources. What do I call it? Variables do. Ooh, okay, it actually got through. So not yet implemented. Bindings, a token identifier X, boom, and the block, push block op. Yeah, so it thought it was a call. Yeah. That's interesting. So it calls X twice, and then plus. Okay, so it parsed it correctly. It thinks that I'm trying to call a function X. So maybe we need to we need to change the op to be identifier, and then the type checker figures out what kind of identifier it is. We'll get there when we get there. So we want to say, okay, well, this is it okay? No, it's some op And then the kind will be op kind. We'll call it binding. And this will take... actually, we need... yeah, so we have bindings. And we'll probably need to wrap the block in a box. So we'll just say block box new block. And then the span is going to be span from to, from the token span. So the token was the initial token that started this branch, which will be the let keyword. And then the final will be the block. So the block span will end at the close parenthesis. So let's add the binding, and then this is probably going to complain because we're moving it. So actually, I can probably move this here, and I don't know if that's happy about it because there's an error up here or not. Okay, so we need to display that. So let's see. Yeah, we got this. So we need to implement display for a binding. Ooh, what does that look like? Bindings block. Because this is used to display in the REPL. So if I was to type a binding in the REPL, what would it show? And I think it should show nothing, or maybe it would show the identifier. Well, you're not really pushing the identifiers onto the stack, so yeah, we won't display anything. Okay, this is where things start to get complicated, because now we have like 3 different targets that are all going to try and use this new op that we've defined. So the interpreter, the REPL interpreter, needs to know what to do. So let's just shut it up and put a to do. The type checker isn't complaining. Do I have a catch-all somewhere? So it would be type check op. It takes the op kind, and I bet I have a catch-all at the bottom here. Man, there's a lot of, yeah, to do. I think that's because, yeah, I gave up on type checking if and choice. So I think I will remove that because the type checking was bad. Add the remaining patterns. Yeah, if, choice, and binding. These two can be to-dos when our compiler or our assembly code is a lot better. So binding. So we have the bindings and we have the block. So what do we want to do? We need scopes. So how do we have scopes? So we will to do this. So if we go to our type checker struct here, yeah, we have all of this state. So we also need to know our... do we need to do any of this? No, because it's just like type checking a block. Yeah. So I think we need to add bindings. And this is just string to type kind because they're only one type. And we need to initialize that with nothing. So it's going to be the same as like type checking a block, except we should maybe... Yeah, it's exactly the same as type checking a block, because you could do something like this. So you could do 5, 6. And you could let x, and you could do x plus print. And so this whole thing would have a signature of takes an int, returns nothing, because you're binding the 6 to x, then you're pushing x, and then you're calling plus, and that's going to then just try to call this. Is that what I want? Maybe. Because this is kind of more flexible, because then you could do this, and then you could then leave something on the stack afterwards. Let's go with this. But for now, let's keep the example simple. And then let's actually leave this example here and just comment it out for now. And so we can come back to that later. So the type checker, we have bindings. So what we want to do is for identifier in bindings, I'm going to say if let token kind identifier name equals that, else unreachable. This is kind of an annoying pattern, but I get why you have to do it, but I wish there was a way of me just like saying, instead of if let, it's just like let and explode if, you know, I got it wrong, so that I don't have to have all this nesting, but it's fine. So we do this, and then we basically want to... how do we type check a block? We type check a block like that. Okay. So yeah, we want to declare all of the bindings, type check the block, and then unbind the bindings, if that makes sense. So that has, yeah, so we want to yoink this, and then we don't want to worry about any of that. Okay, so we have this. So after that, we want to do this, and this will be block. So for each of these, we want to self expect type. So this is going to then on the main type stack in here. For each of these, we're just going to. We're not really expecting a type, are we? We're just popping. And then we run into the same problem that if did. So I'm going to say self pop type. Yeah. Because this might solve it for if later as well. So pop type. We want to match on this. And I believe the type checker might have some... because when we're type checking a block, we don't want to fail if the type stack is empty. Because the problem with type checking if is I was like reaching down into the type stack manually rather than letting it handle the case that you're in a block and you need to be allowed to reach past your stack. Because if you're inside something like this, normally if you dupe on an empty stack, that's an error. But if you dupe inside a function, it's just going to do some type inference on that function. And I think we want to do the same thing. Because if you're in this, let's say you have some function that does a binding, you know, this function now needs to take in an x. So we need something a bit smarter. So let's, I wanted to see struct type checker. Yeah, fail on non-empty stack. No, that's not it. That's for the REPL. Let's just implement it dumb for now, because I've been going for a while and I'm getting tired and I just want this to work. And we can come back and make this work in functions later, because then we'll have it localized in a function that we can then sort out. So if we have some type kind, oh, and it comes with a span. And we don't care about the span. We just want the option type kind. Yeah. And we just want to return that. This is a really stupid function. None to none. Yeah. And we basically want to, in this case, self diagnostics. Yeah, report an error. We can just say format expected value but type stack, or but stack was empty. And we don't even need to format that because there's nothing to format it with. And the span, I think we might have to pass in a span of where we're doing this, and then we return none. Okay, so pop type, and then the span is at the identifier span, because that's the identifier that expected the thing, the type. Okay, so then we have match this, some type kind, great, none, then we just break, I guess. Because we'll have a diagnostic, and we just want to like continue parsing or continue type checking until we finish, and then we can report all the diagnostics. Okay, so now we can just say self bindings, insert name type kind. Boom. Easy. So we're going to do this, and it's going to complain that there is no function x. Pretty sure. Not implemented. Ooh, oh, it would have complained, but we to-do'd. So actually, let's do. What would we be returning? I guess this is its own typed op, right? So I believe you have to return a typed op. And so the kind is a binding with, yeah. Because inside this block, what we're going to end up doing is having a bound operation, which is the loader variable. And then the ins and the outs are the ins and the outs of the block. So this is the signature of this. Oh, you don't like this. Oh. Got to do that. And we need to, oh, actually no, we can just do, this is a typed op. So we have the ins of the typed op and the outs of the typed op. There we go. Fantastic. So we will, I think I need to specify this is a typed op kind for it to actually let me do this. Yep, and now that's complaining, probably because I box up the block before I set those. Okay, and I probably need to have an else unreachable, because it's always a block. Cool. So this is going to complain now that it doesn't have any function called x. Oh. Yeah, and because it fails... Ooh, interesting. Yeah, so it didn't like that. So if I go to... binding... type check block. Yeah, okay. So yeah, type checks the ops. And if we see a... Oh, yeah, because we do it to a call. Yeah. So match self functions name. So let's rename this from call to identifier. Because that's more specific. Yeah. Because then in here we have an identifier. So match self bindings get name. Some... That's not quite right, is it? Type kind is this. And then none match on the functions. There we go. So if we manage to find a type kind for this binding, we do this. And then we'll say no such identifier in scope. So if we do this, we get a to do, because we have a binding, but no function. So now if I go back to this, and I do a little mistake, well, the first one succeeds. Okay, fair enough, whatever. Yeah, let's say this for now. Yeah, so no such identifier y in scope. That's weird that it does the span in the wrong place. Where are we reporting that? Span. Yeah. It's weird that we report it there. And I think I know why. I think it's this thing again. Because we're reporting it there, not there. No. Interesting. Whatever. Not what we're worried about. So, we have... let's fix this again. We have this. And I kind of don't like it like that. Let's do it like this. Let's do it like that. That looks kind of clean. Although... Because it's not really a function, is it? It's a scope. So maybe we should have something like this to differentiate it from being a function. And it's a scope. Something to consider. Because otherwise, yeah, it does look kind of function-y, doesn't it? When really it's being evaluated immediately. Something to consider in future. differentiate it from functions. Yeah, but we'll have to add those tokens and parse those tokens specially. So, yeah. Let's go back to the type checker and make some room. So let's build variables. Get back to where we were. Cool. So if this is that, then honestly, this is super simple. It's an opt type kind variable. They're not really variables because you can't mutate them. So I'm going to call it a value. And it takes nothing in, and it outputs that type kind. And we'll have to clone it because Rust. So we have a new type kind. Sorry, typed op, which is value. And that takes a type kind. Sorry, not a type kind. What do you take? I guess you take a string. Is that true? Maybe. Maybe. Okay. Cool. So we have that. That's just a warning because I don't use it. Okay. Expected int, but the stack was empty. So yeah, okay. This was complaining when we were trying to do the wrong inputs. I don't know why that's complaining. Let's. I think it's because we're inside a block, perhaps. So this was a binding. So for each identifier, self-pop type. Yeah, that's interesting because we passed the identifier span into here. And we pop our type stack. If we find nothing, expected value, but the stack was empty. Oh, we need to peek because this is popping, and then by the time we've popped everything, suddenly the binding is going to expect those ins, so it needs to actually because look, it's the whole binding that expects the int, so we shouldn't be popping the type. So actually that's annoying because this consumes x plus print. Oh, I'm an idiot. This works exactly how it should, because this is expecting an integer because I don't do this. So the reason why that was happening is because this is getting inferred to require another int, but we're not giving it another int. So if I do this, that works fine, because now it's got another int to consume. If I do this, that works fine, because it has enough ints in here to not need to infer that it needs any other arguments. Oh, when your type checker is smarter than you. Oh, good God. Okay. Can you tell I've been at this for hours? But we're almost there. We are almost there. So we don't know how to lower a binding, but that's really easy. So if we go to wherever the hell my lower is, there it is. So we have this. If I get rid of that, what are we not? Okay, yeah, there's a lot we aren't. There's a good reason I had a catch-all, because yeah, we aren't lowering everything yet. So if we have type op kind binding, and this has a block, this will, yeah, we'll have this. So then we'll push. We need to know what's being bound. We need to know what's being bound. So bindings, vector of just type kind, I suppose. In fact, we don't even need that. We just need to know how many there were. So we just need to know n bindings. Yeah. And then this, maybe we're getting a bit, yeah, I think actually this should be a bit more, you know, contain a lot of information. It's only when we get to the lower we start turning them into indexes. So we need to go back down here, and we need to bindings. Well, we need to create a bindings. I already have that. So let's call it let mute binding identifiers. I don't know, man. So when we find one and we successfully match this, we push the name. Vector string found that. Need to clone to get an owned string. Boom. Okay. So in here we have the bindings and we have the block. So for binding, in bindings, we need to store. So we need to let, what would it be, local equals self, next, what was it, next local, and yeah. Yeah, I see a problem coming up, but let's just keep going. And then we just say bytecode push bytecode instruction store that local. Yep. There also might be something interesting with the stack where if we did like let x y and we did like 4 5, x would be bound to 5 and y would be bound to 4 because we're doing things on the stack. Maybe that's fine. Maybe we want it to be the other way around. We can sort that out another time. So for each binding we do that. And then we just want to self lower op the block. So we want to unwrap the block from the box. We have to do a bit of type buggery. There we go. Okay, so this is then going to complain because we're going to hit a binding in here. In fact, yeah, it's fine. It's fine. Namings are fine. We can come back and fix that another time. So that's going to run. We are going to try and lower the block. We're going to hit the typed op kind value, and it's going to say that lowering that is not yet implemented. There we go. So, typed op kind value name. So here's where the issue I foresaw was coming. We need to now match this binding to this name to get the index. And that's easy enough. We can just have a sort of a wait a second, a constant pool. Self constant pool vec of string. No, that's for something else. That's for static like strings and stuff, which we aren't even doing yet, and it's also for function names. We just need a new like hash map, I guess. So LoRa functions, we're going to have bindings, which is going to be a hash map of the name to the index. Now, having it be a hash map to a number makes me think it should be a vector, but I don't care. So when here we want bindings hash map new, and then for every new frame we want to also reset the bindings, because we don't want them to bleed between functions. Cool. So when we push that, we can just say self bindings insert binding clone local, just like that. So then here we just want to say self bindings get. Oh, why does it look like that? Name unwrap. Let binding with that. And then we just want to say bytecode instruction load. And that should be it. It compiled, and we have one local. So if we try and run that, it doesn't do anything. Okay, so what was that? Variables. ASM. This is what I mean. I think my stack arithmetic is incorrect. Because it treats it as a block and it never calls it. Treats it as a block and it never calls it. That's why. Yeah, I think... yeah, we're lowering the block. I think we need to sort of unpack the block, because I think it's doing special stuff to blocks. So we should just say if let typed op kind push block. Yeah. We just need to bytecode extend self lower op for op in ops. Do that. Not extends, extend. I think that will work. That might not be the best way to do it, but we'll give it a go. It worked. I can change that to a multiply, and it squares it. And this is all very annoying now. Let's get rid of this. So we don't really care about the stack frame max locals anymore, because we know that works. So I believe that's in the lower. Yep. Let's just comment that out, because we may need that another time. And then in main, let's only print std error if things go wrong. How about that? And because we did it at the level of the bytecode, the interpreter works as well. So now we have variables. And so let's try the thing that I said. So if we have 4, 5 minus print, and we do that. Interesting. Why is that 5? I think my subtract is bugged. I think my subtract is bugged. Yeah, something's not right with that. I need something else that's commutative. 10 to divide. Does that work? Yeah. Okay. And then if I do 2, 10 divide, get 0. Okay. Something where the commutativity matters. Let A B divide print. We get 0. So if we do 10 to divide print. So you see, like, it's in the different order than you expect, because B is being bound, oh sorry, A is being bound to 2. So we have 2, this is effectively 2, and then B is being bound to 10, so then we have 10. So they're in the opposite order to which you expect. So maybe we want to just reverse it, and because it's kind of more convenient to think, oh, I have like an int and a boolean on the stack, so I want to do IB, maybe. So if we go back to the type checker, which is where we actually do the bindings, and we go to binding, if I just do in bindings iterev, that should be it. That should correctly do it. So now this should be identical to this. And it is. So, I appreciate that was kind of a chaotic session, and we're not quite where we want to be, but we have achieved quite a lot. So we have the ability to store values on the stack, or like on the return stack space, I think it's called, or like on the stack pointer. Like we have stack frames essentially. Every time you go into a stack frame, it will allocate however many locals or space for all the locals, and then it will correctly assign or store and load where those locals are. Where it doesn't work at the moment is calling functions, which has nothing to do with stack frames, to be fair. So the problem I was having is basically I am mixing up my calling conventions. I think we need to go fully stack for calling functions in do. So we shouldn't be using registers. So I think that will be the topic of the next video. But for now, thank you so much if you've made it this far. I appreciate, yeah, that was chaos. That was probably the messiest session so far, mostly because I'm in completely uncharted territory. And I hope this has been entertaining and has been informative. And if you're an expert in assembly language, I'm really sorry at how bad I am at it, but we're getting there. And we have a really nice feature now. And actually, let's uncomment this one, because this should bind 6, add 6 to 5, and then push 11 onto the stack. So let's try that. And with that, I am going to end the video there. Thank you so much for watching. If you made it this far, comment, like, subscribe, all that good stuff. Let me know how you're enjoying Do. Any ideas you have for Do, or like any opinions you have about Do, please let me know, because I'm absolutely loving this project, and I've seen a few people are also really enjoying this as well. So if that's you, please let me know. It's really encouraging to know that you're also enjoying this, and I hope to see you again in the next one. Bye bye.